Welcome to the 24-23 video series. In this video I'll be presenting a little theoretical background to melting points. And we'll start with a review of some important concepts from the previous video on the procedure. And we saw previously that melting range is defined as the temperature at which the sample, as the rate ramps up, just begins melting. So it's the first liquid you notice when you're taking a melting point. And the melting range ends when the very last bit of sample has been melted. So that's the upper end of the melting range, and that's known as the clear point. So you always record melting ranges for samples and melting points when taking melting points. Important to know that the melting range of pure substances, pure organic substances, tends to be very narrow. So pure substances have short melting ranges. And so melting range is an indication of purity. The sharp melting range typically means that you've got a pure substance, although as we'll see that's not always the case, but it's almost always the case. Melting point, recall, we defined as the midpoint of the melting range. There's different ways of defining it, but that's what we'll be using in our laboratories in our course. So melting point is the midpoint of the melting range. So conversely, if you have a broad melting range, that's an indication that you have an impure sample, which is important to know. It's an important bit of information that you would typically get from melting points, from taking melting points. So next thing I want to talk about, so that's a review of some important concepts, is mixtures, taking melting points of mixtures or impure substances. First off, if you have an impurity in your mixture that is not soluble in organic substances, okay, so insoluble impurities. Insoluble impurities do not affect the melting range or melting point. You can abbreviate melting range MR from now on, melting point MP. So what's an example of an insoluble impurity? Something along the lines of, I don't know, a salt. Salts aren't typically soluble in organic substances. Metal shavings, rocks, who knows. So anything that doesn't dissolve in organic solvents or liquid organic compounds. So those will not affect melting points. It's only the soluble impurities that affect melting points and melting ranges. And so how do those do that? Soluble impurities will form a solution with the compound that you're taking a melting point of. And when one of the two begins melting, the other begins dissolving into that. And when you have a mixture of compounds in a liquid, that reduces the freezing point. That's freezing point depression, which is the melting point. And that leads to reduction in the melting point of the mixture. The other thing you notice with impurities, as I mentioned earlier, is you get broad melting ranges. And so for a two-component mixture, there's a way of graphically representing what's happening here that makes this easy to understand. So for a two-component mixture, we can form a phase diagram. Depending on how well I can draw this. It looks something like this. And so at this end we have 100% A and 0% B. And at the opposite end we've got 0% A, so this is composition of our mixture, 0% A and 100% B. And so what you often see, or what you see in these situations, if you have a soluble impurity, we'll say that B is the impurity. Is a phase diagram like this. So in this region we have solid only, so only solid. In this region we have solid A with some liquid B. And in this region we have solid B with some liquid A. So that temperature right there, by the way, the y-axis here is temperature. Let's say degrees Celsius is typical. So that point right there would be the melting point of pure B. And this temperature here would be the melting point of A. So if we have pure A, we have a very sharp melting point, in other words. What if we don't have pure A? Let's say we've got maybe 35% B right here and 65% A. What's going to happen? Well, as we increase the temperatures, we're taking the melting point, the temperature rises, and we've got nothing but solid here until we reach this line right here. This line is known as the eutectic temperature. And that's when you get the first little bit of melting at the eutectic temperature. That's the definition of eutectic temperature, where you first begin to actually, you don't usually see melting at this point. It's the amount of melting at this point is infinitesimal, so you actually physically observe the melting later at a higher temperature. But this is theoretically the point where the melting begins, but it's a very, very small melting. So as we continue to increase the temperature, you begin to see melting. And melting occurs over, as you can see here, and I forgot to label one other region here. This obviously is pure liquid. I mean, not pure liquid, this is liquid only. So it's not pure liquid, it's a liquid mixture, but there's no solid here in this region. So it's liquid A and B only. So as the temperature increases here, we have a melting range. So at some point in here we begin to see melting occur, and melting continues to occur over a fairly broad range until we hit this curve here, at which point this would be your clear point. The last little bit of solid would melt, and increasing temperature above this point, of course, gives you nothing but liquid. You'll have just the liquid solution of the two compounds. So you get a melting range in this region. Now, that's the case with mixtures. You always get broader melting ranges than you get with pure compounds, which you tend to get very sharp melting points. So that would be a very sharp melting point if you had 100% A, a very sharp melting point if you had 100% B. And when you've got very impure mixtures in this region, you get broad melting ranges. Now, you would expect a very broad melting range as you got closer and closer to pure A and pure B here, because you see how big the distance is between the eutectic temperature and the top of the curve. But in reality, in this region close to pure A and pure B, that's these regions here, we've just got a few percent, just a very small amount of A or B present. You tend to see melting ranges, but not nearly as broad as this. And the reason is that there's such a small amount of B or A over here that you don't notice that melting. So you'll get a depressed, I didn't show the depression here very well, you'll get a depressed melting point. Should have drawn this as a better curve up here. You'll get a depressed melting point, and you'll get a melting range, but it's not as broad as you would expect from this diagram, if that makes sense. Okay, so, but if you get very impure mixtures in this region, you tend to have very broad melting points and depressed. And again, this curve should come down more. You always see depressed melting points with mixtures compared to the pure compound, as long as they're soluble in each other. That's what we're assuming in this diagram. One more important feature of this diagram is this point right here. That point is known as the eutectic point. So you'll note that if you're at the eutectic point, the eutectic composition is the composition that corresponds to the eutectic point, and you increase the temperature here, once you reach the eutectic temperature, you get a very sharp melting point. That is, if you go beyond this, you have liquid only. So it's possible to have a mixture, a very impure mixture, that has a very sharp melting range, if you are just by chance at the eutectic composition, which is unlikely, but it's possible, so that's something you have to bear in mind. So it is possible for very impure mixtures of mutually soluble compounds to have a sharp melting range if you're at the eutectic point. So that's a very brief overview of the background and theory of taking melting points. So we now know why we see melting ranges for impure mixtures and why sometimes the ranges aren't as broad as we think they should be, or they should be if they're impure, if you got a mixture. And also why we get reduced melting points. So make sure that you've seen the procedure video before you do the laboratory. You're supposed to watch the procedure, of course, before you do the lab. And I will see you in lab.